Okay, everybody, welcome to Keen and Can Do Learning to Program C, Episode 5. Let's get into it. We left off with Chapter 7 of the Learning to Program C Codeahoy book that is released with the Creative Commons license. So I'm sharing this under that license. We left off with integer operators. We'll quickly review what we did before that, which was essentially learn about the different integer types and the sizes of those, that being char, short, int, long, and long. We talked about how two's complement works and talked about the different fixed width types and like the minimum types or the maximum size types for if you're trying to optimize for space or optimize for speed. We talked about using the size of operator. We talked about naming constants. And we talked about the different ways that numbers can be implemented in a computer. Binary, decimal notation, octo, hexadecimal, and then character constants. So we'll pick up, as I said, with integer operators. Let me turn on my monitor here. And then we will get going. Let's do properties here. I'm going to change it to headphones, USB audio device. And then let's do monitor. Oh, no. That's not that. One moment, I have to. Okay. And media source. I wanted to monitor, but I'm not going to be able to monitor today, I suppose. Okay. So integer operators. Arithmetic operators. The usual addition, negation, or subtraction and multiplication operators work on integers pretty much the way you'd expect. The only caveat is that if the result lies outside of the range of whatever variable you are storing it in, it will be truncated instead of causing an error. Unsigned char C. C minus 1, C equals 255 plus 255. Set C equal to 254. C equals 256 times 117, set C equal to 0. Negative 1, set C equal to 255, because it's an unsigned char. So using the 2's complement, we know that negative 1 is the same as 255. So it goes from 0 to 255. This can be a source of subtle bugs if you aren't careful. The usual giveaway is that values you thought should be large positive integers come back as random looking negative integers. Division of two integers also truncates. 2 divided by 3 is 0, 5 divided by 3 is 1, etc. For positive integers, it was always round down. Prior to C99, if either the numerator or denominator was negative, the behavior was unpredictable and dependent on what your processor chose to do. In practice, this meant you should never use divide if one or both arguments might be negative. The C99 standard specified that integer division always removes the fractional part, effectively rounding towards 0. So negative 3 divided by 2 is negative 1. 3 divided by negative 2 is negative 1. And negative 3 in parentheses divided by negative 2 is 1. There is also a remainder operator, modello, with example 2 modular 3 equals 2. 5 modular 3 equals 2. 27 modular 2 equals 1. The sign of the modulus is ignored, so 2 modular negative 3 is also 2. The sign of the dividend carries over to the remainder. -3 modular 2 and -3 modular -2 are both -1. The reason for this rule is that it guarantees that y is equal to x times y over x plus y modulo x is always true. Okay. Bitwise operators. In addition to the arithmetic operators, integer types support bitwise logical operators that apply some Boolean operations to all the bits of their arguments in parallel. What this means is that the ith bit of the output is equal to some operation applied to the ith bits of the inputs. The bitwise logical operators are tilde, bitwise negation used with one argument, as in tilde 0 for the all one's binary value, and bitwise and, bitwise or, and bitwise XOR sum mod 2. These are mostly used for manipulating individual bits or small groups of bits inside larger words, as in the expression x and the hexadecimal value 0f, which strips off the bottom 4 bits stored in x. Strips off the bottom 4 because A, B, C. Examples. X is the binary value 0011 or 3, and y is the binary value 0101 or 7. No, 5. Expression x and y. X and y is the value 0001, which is 1. How does that exactly work? Wait a second. So if I write, let me see over here. So if I go to scratch. So if I'm over here and I have 0011 and 101, it's not addition, it's and. So how's, in addition to the arithmetic operators, integer types or bitwise logical operators that apply some Boolean operation to all bits of their arguments in parallel. What this means is that ith bit of the output. Oh, okay, so the and is 0 and 0 is true. 0 and 1 is one. 0. I don't. How does that work? How does that get that value? So that's 0. That's 0. That's 1. Okay, so then this one's 0011, 0101. So that would mean that X or Y is, my son's Steam is always coming up. Thinking about putting Linux on here very, very, very soon. Okay, so we have 0 or, so or would be 0, 1, 1, 1. Okay, so that one I understand. This one I have questions about. This one I understand. Okay. X and Y. X let's do an org file. Let's do bitwise.org. Okay. Bitwise operators. We'll do X, Y, expression. Let's do var value do that. Hold on. Oh, I thought that. Okay, it doesn't matter. Okay, so do X value Y 0 result, and the result is okay. 0 1 0 1. Okay, so it'll be 0 1 1 1. So I guess I understand. And then X to the Y. The shift operators shift the bit sequence left to right. following program is an example of this technique. For example, called logical operators. But when do you use bitwise in general as well? So let's go back to bitwise again. In addition to arithmetic, integer types support bitwise logical operators. It applies some Boolean operation to all the bits of their arguments in parallel. Is that the ith bit of the output is equal to some operation applies to the ith bit of the input. So is this assumed that 0 equals false and 1 equals true? Because then we get false and false is false. False and true is false. False and true is false. True and true is true. Okay. Okay. So or. False or false is false. False or true is false. False or false is false or false is false. False or true is true. False or false is true. True or true is true. Okay. I think I'm starting to understand now. The bitwise logical operators are so let's do the and then bitwise and bitwise XOR, i.e. sum of mod 2. Individual bits or group of bits. XOR. Not quite sure. Bitwise XOR. Bitwise XOR. Bitwise 2. The result of XOR is 1 if the 2 bits are different. Okay. The result of XOR is 1 if the 2 bits are different. Very interesting. Okay, so we have X or Y. XOR. Okay. Just or. That one's and. That one's or. That one's XOR. Okay. So bar value X 0011 Y 0 1 0 1. Okay, result that is 0 0 1 1 0. Yes, good job. Okay. All right. And negation. Negation. Not sure about that. X and which strips off the bottom 4 bits stored in X. I'll have to see why that does that, but let's do the negation and X. Negation. Okay, so we have bar value X 0011 Y 0111 and result negation 0 negation. So, that'd be, what's the negation? Bitwise negation. Bitwise negation. Oh, that's not. Not negation. Okay. Not negation. Oh. Is the stream even working? It says excellent connection, but it's not showing chat. Okay. Not. Okay, so not. C takes one number, inverts all bits of it. Inverts all the bits. Okay. So it's inversion. Inversion. Oh, just X. Okay. Negate X would be 1100. Okay. Now, but I still want to understand why do we have that this? Still want to understand why we have X and 0x0f. Strips the bottom 4 bits stored in X. Let's we'll ask ChatGPT about this in a little bit. Okay. The shift operators, left shift and right shift the bit sequence left or right. X left shift Y produces the value X times 2Y, ignoring overflow. This is equivalent to shifting every bit in X, Y positions to the left, and filling in Y zeros for the missing positions. In the other direction, X shift to the right Y produces the value X times 2 minus Y by shifting X, Y positions to the right. The behavior of the right shift operator depends on whether X is unsigned or signed. For unsigned values, it shifts in zeros from the left end always. For signed values, it shifts in additional copies. It shifts in additional copies of the leftmost bit, the signed bit. This makes X right shift Y have the same sign as X if X is signed. If Y is negative, the behavior of the shift operators is undefined. Examples: unsigned char X. Left shift shifts every bit in X, Y positions to the left. Okay. Yeah, okay. And then shifting it to the Y. 3. Ignoring overflow. So it fills in with zeros. Okay. Okay. But if it's sign char. So it's just talking about if it's negative or not. Okay. We'll have to revisit that later. Okay. Shift operators are often used with bitwise logical operators to set or extract individual bits in an integer value. The trick is that okay. Contains a 1 in the ith least significant bit and zeros everywhere else. Are often used with bitwise logic to set or extract individual bits in an integer value. The trick is that 1 left shift I contains a 1 in the ith, shifts x, shifting every bit in x, y contains a. How is this possible? The trick is that one left shift I contains a 1 in the ith least significant bit, and zeros everywhere else. So x and 1 shift I is non-zero if and only if x has a 1 in the ith place. This can be used to print out an integer in binary format, which standard printf won't do. Ah, okay. We need to watch a video. Let's watch video later on the logical. They're called logical bitwise operators and bit shifting. On the bitwise operators and bit shifting. Okay. The following program gives an example of this technique. For example, when called as test binary 123, it'll print followed by a new line 123. There's 2. Where's your 3? 1, 2, 3, 4. 2, 4. An integer in binary format. How is that binary format? Is that binary format? 1, 1, 1, 0. 0. 2, 4, 6, 8, 16. Okay, so we have 1, 2, 3. Include standard. Print out all bits of n. Void print binary unsigned int n. Unsigned int mask equals 0. This grotesque hack creates a bit pattern 1000, regardless of the size of an unsigned int. Mask equals not mask XOR not mask shifted for mask in the other direction. We can set the ith bit of X to 1 by doing XOR or to 0 by doing X and see the chapter on bit manipulation for applications of this to build arbitrary large bit vectors. Bit manipulation. Where is it? Oh, so it's not a thing? But it will print 1, 2, 3. Least significant. Print binary. Huh. The following program is an example. So what I think this is in binary is 16 and 8 is 24. So that would be plus 16 plus 8, 6, 2, 32. So how is that 123? I don't understand that program. Okay. I can't get my chat to show up today. Not sure why it's not showing up. Okay. Okay, so we have logical operators. To add to the confusion, there are also 3 logical operators that work on the truth values of integers. Where I still don't understand why. Print binary 1, 2, 3, it would print this. That's not right. Oh. Did you miss a? Yes, that's a typo. That's a typo. It should be 1 and 32. Then 60, but that's 64 still. Not 123. Well, how is that 123? How is that 123? Let's see. Mm-hmm. Five. Still not understanding that. Two, 3, 6, 7 bits. Yeah, 64. Oh, that's not 6, that's 8. Oh, I made a mistake. That was my bad. That's my bad. 2 base, not... I don't even know what that is. Oh, come on, Keenan. $123. Now it makes sense. But here, it's typoed for sure because it's missing a bit, and this is in the wrong spot. Unsigned int. Unsigned int. Unsigned. Okay. To add the confusion, there are also 3 logical operators that work on the truth values of integers where 0 is defined to be false and anything else is defined to be true. These are and, or, and not. The result of any of these operators is always 0 or 1. So not x, for example, is 0 if x is 0, and 1 if x is anything else. The and or operators evaluate the arguments left to right. Ignore the second argument if the first determines the answer. This is the only place to see where argument valuation order is specified. So 0 and execute programmer. 1 or execute programmer is in a very weak sense perfectly safe code to run. Watch out for confusing evaluate arguments left to right. Ignore the second argument first determines the answer. Yeah. Watch out for confusing and with and. The expression 1 and 2 evaluates to 0 because it's bitwise. Yes. Evaluates to 0, but yes, does it evaluate to 0? Let's see. Watch. Using and. Example 1 and 2. Okay, so let's do bar. Value to x 1 to 0 1 y 2 result would be false and true is false, false is true. Oops. Which is 0. That makes sense then. Yes, you get down to the values of the bits and this stuff. That's why I'm taking these notes, because this stuff is it's kind of complicated for me, but it's going. It's going. It's fun. I can't get my my chat overlay to work. Let me, you know what? Let me completely remove it. Remove. And then I'll add another one. Let me chat. And then do that. Refresh. It's like 400. There we go. Nice. I don't know what the issue was with it. Where's the transform where I do the I was thinking about scheduling it, but subtract? No. That's not what I want. Oh shit. Fail. 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 Screen? Oh yeah, there we go. Can you see the text okay though? Let's do properties. Let's do font. Color. Margin. Background color. Font color. Color, let's do color. What would come up good on that gray? Color blue. No, that didn't really. I have to see what the inspect. I have to see what I'm gonna do is trying to see if we can find out what one of these font values are. Message. Font. Where's the color? Where's the computed? Computed. The color. No, the color. There we go. RGB 255. Computed. I have to do. Wait a second. Do CSS values have to be CSS values? Do they have to be strings? Oh. No, no. What about colors? Color. Is it a string? No. Background color. Where's the named colors? CSS named colors. There it is right there. Okay, so properties. Do orange. It doesn't make it orange. Test. No, it didn't make it orange. Huh. Oh, maybe important. Let me set important. Are you familiar with important yet? What this thing? Properties. Color. Color important. Oops. Stop. No. Bing, get it away. Color important. There we go. Orange. Important. No. Testing. I don't know. I'll have to look more into that later. Okay. So yeah, the logical operators, that does make sense. So the expression 1 and 2 evaluates to 0 because in binary it's 0, 1, and y it's 1, 0, and 0 or false and true is false, and true and false is also false, which is 0. But 1 and 2 evaluates to 1. The statement, because true, the statement 0 and execute program is also unlikely to do what you want, right? Because whatever the binary representation of this is could get kind of hairy. Yet another logical operator is the ternary operator, where x, y, or z evaluates the value of x is non-zero. Yep. Ternary. So what this says, ternary operator says, file exists, bad file. So if that returns true, then you delete the file. Otherwise, you create a file. So it's kind of like a shorthand for writing if this, then that, right? Else, something else. The convention that Boolean values in C are represented by integers means that C traditionally did not have an explicit Boolean type. If you want to use explicit Boolean types, you can include the standard bool.h header file added in C99 with hashtag include standard bool.h. This doesn't give you much. It makes bool an integer type that can hold Boolean values and defines false and true to be constants 0 and 1. Since bool is just another integer type, nothing prevents you from writing x equals 12 divided by true or similar insults to the type system. But having explicit bool, false, and true keywords might make the intent of your code more explicit than the older int 0 or 1 approach. Relational operators. Logical operators usually operate on the results of relational operators or comparisons. These are double equality, not equal, inequality, less than and greater than, less than or equal to, and greater than or equal to. So for example, if size is greater than or equal to minimum size and the size is less than or equal to max size, then put's just right. Okay, test if size is in the inclusive range, minimum size, max size. Beware of confusing double equals with equal. The code danger if x equal 5 is perfectly legal C and will set x to 5 rather than testing if it's equal to 5. Because 5 happens to be non-zero, the body of the if statement will always be executed. This error is so common and so dangerous that GCC will warn you about it. Okay, so truthy values then are always greater than 0? I am guessing? Because otherwise that doesn't make sense. Otherwise that doesn't make sense. Okay. Converting to and from strings. To input or output integer values, you would need to convert them. We'll warn you without any tests that look like this. If you use the wall option, some programmers will go as far as to write the test as 5 double equal x, just so that if their finger slips, they will get a syntax error on 5 equals x, even without special compiler support. Oh yes, because 5, yes. Yeah, because that's, first off, that's an illegal identifier. Oh, I like that. Converting to and from strings. To input or output integer values, you would need to convert them from or to strings. Converting from a string is easy. Oh, I think I can do something real quick. Audio. Monitor. Where's monitor? Okay, now I am monitoring. Okay, cool. So I can hear the mic. I can monitor. I can hear most of the stuff. Let's see. Do I want to monitor my mic? See how late that is. Okay. Now I'm monitoring my mic. It's actually not bad. It's kind of weird hearing my voice, though. Let's go ahead and turn the monitor off. Okay. That'd be interesting for, like, if someone else was helping you. All right. To input and output is usually done using print. To input or output integer values, we need to convert them from or to strings. Converting from a string is easy using the a2oi or atol functions declared in standard lib.h. These take a string as argument. What is that function for? What? So let's see. Ah, I just moved my OBS. Okay, so let's see. Is there an info page on ATOL? No, is there? Oh, yeah, I gotta go to Ubuntu. Okay, info ATOL. It will convert a string to an integer. Features test script. The ATOL function converts the initial portion of the string pointed to by n pointer to int. So int constant char n pointer. The behavior is the same as constant char. Okay. Declared in standard lib.h. These take a string as an argument, return an int or long, respectively. C99 also provides atol for converting to long. These routines have no ability to signal error other than returning 0. So if you do A2OI Sweden, 0 is what you will get. Output is usually done using printf. An error other than returning 0. Okay, well that could be an error. Oh, that's not an error because in your main functions you return 0. So that wouldn't be an error, would it? Output is usually done using printf or sprintf if you want to write to a string without producing output. Use the %d format specifier for ints, shorts, and chars that you want the numeric value of. %ld for longs and %lld for longs. So here is where we get the help for the stuff from a few days ago. Specifically for %d, %ld, and %lld. Okay. The contrived program uses all these features given below, include standard lib. This program can be used to show how ATI handle overflow. For example, try overflow. Boom, 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 boom. Very interesting. Okay. Next, because it's going to do overflow stuff. Next is floating point types. We are getting somewhere. We're getting somewhere. All right. That's probably enough for tonight. I wanted to ask ChatGPT about this though, didn't I? Remember? So let's ask ChatGPT. Okay. Oh, and then we had a few. Remember answers I had. Okay. Oh, the 4 and 6. 4, 5, and 6. I think I might save those problems for work on tomorrow. We can talk about this one. So conversion between signed and unsigned. So let me visit it. I do want to answer these questions, but let me ask this one from ChatGPT first. Help me understand this. Oh, only the last 4 bits of X are retained and the rest are set to 0. This is because the bitwise and between 1 and 1 is 1, and between 1 and 0 or 0. Between 1 and 0 or 0 and 0, 0. So this expression effectively isolates, strips off the bottom 4 bits of the variable x while setting other bits to 0. Yeah, because it doesn't matter what those are. Okay. Yeah, because it would be okay. Okay, so let me fully understand this. Okay. With Chat GPT's help. Okay, so let's say x equals I don't know, 1, 2, 3, 4, 5. Okay. All right. So and we know 0x 0 f is 1, 2, 3, 4, 1, 2, 3, 4. So we get 2, 3, 1, 2, 3. Wow, that's cool. Okay. All right. And what else do we want to talk about? Let's end it today. We'll pick up on chapter 8 on our next stream. Thanks you guys for joining in. Hope we learned some stuff together. Subscribe if you like that kind of stuff. And I am thinking about doing a schedule on my next stream, possibly posting my Discord server, so we can build up this community of learning to program in C. If you're watching the video later and you want to give me some ideas or some tips and tricks, feel free to. That's all I have for today. Thanks for watching Keen and Can Do. Until next time, goodbye.